Okay, so I would like to talk a little bit about the limits of our modeling and the limits of how we think about things, or if you want, we can call it dancing with infinities, or to be more precise, dancing around infinities, which we will do quite a bit in this class. It's some form or shape. So the basic observation is that, think about a finite program. What is a finite program? It's a program that uses a finite amount of memory, right? So think about, 1 kilobyte of memory, right? This is all the program has, right? So if a program has a finite amount of memory, then the number of states the program might be in, right, when you run it, when you execute it, is going to be finite, right? Because you can just write down explicitly the different states for every bit in the memory. You can write down what states, what the value of this bit in memory is. You're going to get a large space, but, this is a finite number of states, right? So in particular, if you're using k bits, you are going to have something like 2 to the k different bits. Now, I'm ignoring here low-level technicalities. That program, the state is not only the memory, it's also, what the value of the registers and stuff like that. Let's ignore this for the time being, because I want to keep things simple. Now, if you think about this 1 kilobyte programs, then, it has 124 bytes. Every byte is 8 bits, so we get roughly 8,000 bits. Right. Well, height. Let's do it exactly. 8192, maybe. Let's see. Yes. Yeah, seems about right. Okay, so this is the number of bits that you get in 1 kilobyte memory, which means that the number of states is 2 to the power of this number. This is a pretty large number. It's roughly something like 10 to the 800, right? Which for all, it's a huge number, but it's a finite number, right? So a program that uses a finite amount of memory as such is just a DFA. Right. We can think about it as a DFA, and the reason why we care is because if something is a DFA, we can do things with it which we cannot do with regular programs. Right. For example, given a DFA and given an input, I can tell you whether the DFA stops on this input. I essentially just run the DFA on the input, and I see whether it gets stuck or not. On the other hand, I cannot do this with regular programs, right? Because regular program can do very weird things like duplicate themselves, use a huge amount of memory, much bigger than the input, etc., etc., etc. So, we don't know, when we run a program, we don't know how long we have to wait before it stops, right? It's like waiting for Godot, we can wait forever and it will never stop, right? While with the DFA, we know immediately where it stops. It stops when it's done reading the input, right? It's this immediate feedback machine, which is a nice property of DFAs, right? In particular, Turing's famous theorem, which we'll come back to it later in the course, is that if I give you a program and I give you an input, it's not possible to decide whether the program stops on this input, right? So programs and DFAs are fundamentally different creatures. We can do things for DFAs that we cannot do for programs. DFAs are much simpler at some point. Okay, so now the number of atoms in the universe is, according to Wikipedia, 10 to the 82. Whatever it is, it's a finite number. As such, assuming that every bit, every atom in the universe can store only a finite number of bits, this immediately implies that every program you run in this universe is going to use a finite amount of memory, and as such, it's a DFA. So all programs in this universe are just DFAs, right? And as such, checkmate, mate, right? It means that all this nonsense about programs and so on that Turing came up with is completely irrelevant, because everything is a DFA. Or if you want to put it differently, what is this nonsense, right? So really what's going on is that our model, we have a theory, and the theory tries to capture the world, right? It oversimplifies it. It tries to capture the world, right? And one needs to apply this theory in a clever way, avoid applying it where it's not necessarily useful, right? Sometimes it's not clear where applying a theory is useful or not. You just have to try it and see whether the answer you get is useful or not. But that's what we have to do here now, right? Because, think about my example of a program that uses 1 KB of memory, right? The number of states it has was something like 10 to the 800, which is way, 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 way bigger than the number of atoms in the universe, right? So to all practical purposes, if we want to think about a program that uses 1 kilobyte of memory as a DFA, in a dumb way, then the number of states is enormous, is gazillion, and for our practical purposes, for us, it's infinite, right? So really what's going on is that if we are dealing with really large constants, right? If we deal with really large constants, then for our practical purposes, they're infinity, and as such, when we have a theory that can deal with unbounded quantities, we can use it in such setting, and it's useful for us. Okay, so the main thing I want you to take out of this is to know where to be skeptical when you can apply a theory, and also be skeptical of when you get an answer from theory and you say, okay, this doesn't agree with the universe as I know it, to realize that this is okay. This is the limits of what theory gives you. It's not necessarily useful, but it gives you a lot of useful way to think about things.